Okay, so I was thinking about doing an introduction to graph theory. I mean, it's not like I know very much, but I do know quite a bit. So, I mean, like basic graph theory. So, a graph is something that looks a bit like this. Okay, no, that's not particularly specific, but okay, go with me. So this is a graph. In fact, this graph is called P3. So a graph has vertices, and those are these things. And it has edges, so those are these things. And so we can write graph G as a pair of vertices and edges like that. And by the vertices, like a set of 1, 2, and 3. And the edges are 1, 2, 2, 3. As easy as that. So why do we care about graphs? Well, we use graphs when we want to use local properties. For example, things you can tell just from looking at this vertex here, and then deduce global properties, like what can you tell me about the graph as a whole? Is there any way I can just look at the vertices one by one and then tell you what the number of edges is? And turns out there is, and it's called the handshake lemma. So what the handshake lemma says, so if I draw it like this, lemma, it says that if we look at each of the vertices and look at how many edges are next to it, so there's, in this case, and we call this a degree of the valency. Degree of 3 is equal to 1, degree of 2 is equal to 2, because there's 1, 2 edges next to it. Sorry if it's getting a bit messy. But you can see that degree of 1 is equal to 1, degree of 2 is equal to 2, degree of 3 is equal to 1. So I'll just draw the graph over here again. Nope. So look like this, 1, 2, and 3. And now if you add up the degrees, what you'll notice is that if we add them up, we get 4, and that actually turns out to be 2 times the number of edges. So the number of edges is 2, so E equals 2, 2 times E. And it turns out this is always true for every graph. So the way we could write it is the degree, so the sum of the degrees is equal to the number of edges. Oh, sorry, not just number of edges, 2 times. If you notice, this is 2 times the number of edges. Okie doke. And this is the handshake lemma. Okay, so why is this true? And so, in other words, what is the proof? So the proof goes like this. So if you have any two vertices, and they have an edge between them. So any two vertices has an edge between them. Let's call this vertex I, vertex j. Then we'll have an edge ij between them. And so over here, we're counting this once and this once, because over here we say it's I is next to j, and over here we say j is next to I, which is basically the same thing. And so we end up counting each edge twice. So count, I don't like writing big words, CTS, that's continuous. Counts edge, oh no, edge 2 times, that's 2x, twice, there we go. So this should be D, let me just fix that. E, D, G, E, count each edge twice. So that was pretty easy. I mean, yeah, that's pretty easy. Okay. So the reason that this works is because when we look at the degree, we count each edge twice. And we also count every edge, so that's also important. Every edge will be at least next to, and will be next to at least two. I mean, next to exactly two vertices. Okay. So what next? Okay, so the next thing which is important is the notion of a subgraph. So let's let G be a graph. B a graph. We say that H is a subgraph if it is a graph if it is a graph, so it has to be graph 1, and the vertex set of H is a subset of the vertex set of G, and the vertex set of, the edge set of H is a subset of the edge set of G. It should be G. What am I on? Okay, there we go. These two things must hold. So it has to be a graph because, for example, if you had a vertex like this, you can imagine just getting rid of this vertex. Sorry, if G was this, then you can imagine getting rid of this vertex. These two would hold, right? But this is not a graph because an edge has to go between two vertices. And for example, this would be a graph. So whenever we get rid of a vertex, we have to make sure we always get rid of every edge next to it as well. Okay, so that's a subgraph. So let's look at this graph over here. And we will notice that this week, if you recall, I call it P3. This over here is P2. And so we say P2 is a subgraph of P3 because we can get to P2 by removing this vertex and this edge. Okay, maybe one more example on that. So next, this one's a path graph, that's why I call it P. It looks like a path, right? Next one's would be called a complete graph. So a complete graph is when, if you have edges, vertices, you draw every single edge that you possibly can, right? And so this is what we call K4, complete graph of 4 vertices. Or a nice theorem, it's pretty easy to prove, is that the number of vertices of a complete graph, the number of edges of a complete graph is the number of vertices times the number of vertices minus 1 divided by 2. I mean, we can just do that, right? I mean, so what we have, what do you call it? I mean, one way you could do it is if you can say this is 3, and then actually, no, that requires a lot of thinking. Why don't we just use the handshake lemma, right? If there's an edge counting question, we can just use the handshake lemma. So the handshake lemma tells you that if you sum the degrees, if you do the sum of the degree of the vertices, then that's equal to number of edges. To twice the number of edges. Okay, so if I sum the number of the degrees, the degrees of every vertex is 3. So in fact, the degree of every vertex is actually 1 less than the number of vertices, because every vertex is connected to every vertex apart from itself. So the degree of V, vertex V, is equal to n minus 1, where n is the number of vertices, okay? And now we're summing over all the vertices, and there's n vertices, and so we get n times n minus 1 as the sum of the degrees. So the sum of the degrees Sum of the degrees is equal to n times n minus 1. And we know that's equal to twice the number of edges by the handshake lemma. And so if we equate them, we get that number of edges is equal to n times n minus 1 divided by 2, as required. Okie dokie, so I hope you enjoyed this video. I mean, maybe there'll be more graph theory to come.